Welcome everyone. For today's prep, we're going to be looking more at Maclaurin series. And we're going to start with just a few of our basic examples that we've looked at for Maclaurin series. So the first three here, we've got e to the x, sine x, and cosine x. And we actually, in the previous section, we actually went through and constructed the Maclaurin series for the exponential and sine. So the exponential, this is the one that has x to the power n over n factorial. Sine of x has just the alternating odd powers of x. And what we're going to see, excuse me, is that cosine has all of the alternating even powers of x. So we're actually going to do the Maclaurin series for cosine. We're not going to construct it in the traditional sense of just going through and calculating all the derivatives. We're going to prove it using our Maclaurin series of sine of x and a little bit of calculus. Now, these aren't the only Maclaurin series that we've considered. A few more important ones, and probably the one that really started us on this idea of representing functions as a power series was our geometric series. This is the one that we really started with, this 1 over 1 minus x function, and representing that as the sum of x to the power n. So this is the one we've really worked quite a bit with. And what did we find for our radius of convergence for that one? Well, for this one, the radius of convergence was 1. Now going back up, we found for these other ones, e to the x, sine x, and what we're going to find, all of these have a radius of convergence of infinity. So these Maclaurin series essentially converge for all x values. Whereas with this geometric one, there's some limitations. Doesn't work for all x. And we have here the Maclaurin series for inverse tan and natural log of 1 plus x. And I think we did this one, and we proved this using, you could actually go through and just do the Taylor series construction. You could also prove this using some calculus and this, what we know about this function 1 over 1 minus x. Same thing with inverse tan. So both of these you could prove using this as like your starting point. So all of these also have a radius of convergence of 1, because in some way they're related to that geometric series. All right, so we're going to keep these in mind. We'll refer back to them as we need to, but let's start. We're going to look at an example here, and we're going to use the Maclaurin series for sine of x to find the Maclaurin series for cosine x. And then we'll, kind of spoiled it. We'll state the radius of convergence as well. All right, so let's keep our Maclaurin series for sine of x in mind, but we're interested in the cosine function, cosine x. And we're interested in using sine of x as the starting point for our power series. So how is cosine related to sine? Well, if we integrate our cosine function, the integral of cosine is sine. And once we have sine here, we know what the power series representation is, the Maclaurin series representation for sine. So we can get our power series rep for sine of x. So we know that this is the sum from negative 1 raised to the n, x to the 2n plus 1 over 2n plus 1 factorial We're doing the sum from n equals 0 to infinity. And we started by integrating the cosine function. So we have our power series representation for sine. We have to go back. We have to undo that integration. So this is kind of familiar to what we did with that function 1 over 1 minus x. We looked at some derivative and integral problems there. So if we want to undo this integration, we're going to do the derivative. And the nice thing about differentiating a power series, when you have the coefficient terms separated off, these constant terms separated off, you can focus in on just doing the basic power rule on your power of x term. So if we do our power rule, we're going to take the exponent, bring it down, get 2n plus 1. Subtract 1 in the exponent, so that'll make it x raised to the 2n. And then we've still got our 2n plus 1 factorial in the denominator. But we can simplify that factorial term. So this was just the derivative, our basic power rule, our derivative power rule. And then we still have these coefficients. All right, so let's simplify the factorial term here. And if we remember, 2n plus 1, 2n plus 1 factorial, let's turn the page. So we're seeing the top page here. Let's turn the page, and that's 2n plus 1. And what's one page lower? Well, it's just going to be 2n. And we've got all the remaining pages. So we've got the rest of our book there, the factorial. And we see that we've got a 2n plus 1 on the top, 2n plus 1 inside the factorial there. So those are going to cancel if we want to simplify this. And that's going to leave us with just the 2n factorial. So we end up with the sum from n equals 0 to infinity, negative 1 raised to the n, x raised to the 2n over the 2n factorial. And this is our power series representation for cosine. So we're using that same strategy that we looked at with some of those 1 over 1 minus x type functions. And let's just check. How does this look? So if we go back, yeah, looks spot on. There we go. Now, one thing that we saw, when we differentiate, sometimes that n equals 0 term does disappear. But what we did is we had the power series representation for sine, and that n equals 0 term was x. So when we differentiate the n equals 0 term in this case, it doesn't disappear. It actually sticks around because that very first term, the n equals 0 term, does have an x in it. So that's why the starting index of cosine here is still n equals 0. If we were to differentiate e to the x, well then maybe you would change because that starting index would disappear. But then you actually could reindex it and restart back at n equals 0. But just a little note there about our starting index for sine and cosine there. All right, so what about the radius of convergence? Well, what we've seen is that we actually calculated the radius of convergence for our sine of x power series. So we used the ratio test for that. And we found that it was infinity. So this one's not related to a geometric series, so we did have to use the ratio test. But now that we know the radius of convergence for sine of x, the sine of x Maclaurin series, when we differentiate, differentiation doesn't change the radius of convergence. So we just make note of that. So that's a nice thing about the radius of convergence. It doesn't change with differentiation or integration. So that means our radius of convergence for cosine is also going to be infinity. So this power series converges for all x values. Nice. All right. Let's look at another example. So now that we have the Maclaurin series for cosine x, let's use it to actually construct the Maclaurin series for a more complicated function. All right, so we've got this function x cubed times cosine 2x. And we're going to start, we've got the x cubed part. That's just a kind of a basic power function that we're multiplying. And then we've got this cosine 2x. We're going to start with that. And we're actually going to start with plain old cosine x. So let's start with the Maclaurin series for cosine x, the one we just found. So this is going to be the sum from n equals 0 to infinity, negative 1 raised to the n, x raised to the 2n over 2n factorial. And what we're going to do, if we look at our more complicated piece here, it's cosine of 2x. So 2x is the inner function. So what we're going to do is we're going to plug in that inner function. So we're going to plug in 2x. So that'll give us cosine of 2x. And wherever we see an x in our Maclaurin series here, we're just going to change it now to 2x. So when we do that, we'll have the sum from n equals 0 to infinity, negative 1 raised to the n, and then instead of that 2x, or instead of the x, we're going to write 2x. And it'll be 2x raised to the 2n divided by the 2n factorial. And when we do this, good idea to separate any constant terms from variable terms. So let's separate that off. So we'll have n equals 0 to infinity. We've got our negative 1 raised to the n. And when we separate, we distribute the exponent. So this 2n is going to go to the 2, and it's going to go separately to that x. So we'll have 2 raised to the 2n times x raised to the 2n all over our 2n factorial. And this, again, all we did is we changed the x to 2x. So we identified the inner function, and we plugged it into the Maclaurin series for 2x, or for cosine x. Now, we have our Maclaurin series for this cosine 2x. Now we have to incorporate this x cubed. So now we're going to multiply by x cubed. So when we do that, x cubed times cosine of 2x. So we'll initially put the x cubed outside our summation, but we'll be able to bring it on in. So we've got the x cubed sitting on the outside there. And one of our properties of series is that as long as our series is convergent, we can distribute. And we can bring this on in. And when we bring our x cubed in, we're just going to add it to the powers of x there. So we get the sum from of negative 1 raised to the n, 2 raised to the 2n, x raised to the 2n plus 3. So again, we add exponents there. And then divided by the 2n factorial. And there we go. We got our Maclaurin series for this function x cubed times cosine of 2x. All right, so we're going to practice more of these in class where we kind of take one of our starting easy Maclaurin series and we kind of build it up from there. So I think the next one we're going to look at involves, let's see. Yeah, it's going to involve e to the x, but we're going to look at this more complicated function, e to the negative x squared. All right, so we'll see you then. Bye-bye.